Recursive functions are a special kind of function that calls itself. So when we talk about recursive functions, and especially when we're converting them to assembly code, we want to think of them in the first pass as if they aren't recursive, as if it's just calling another function. And then we're going to think about, as a second pass, well, which registers do we need to save and restore on the stack to make this work? So here's an example recursive function. This is the factorial function. Factorial of n equals n factorial. And that is n equals n times n minus 1 times n minus 2 times n minus 3, blah, blah, blah. So for example, factorial of 6 is 6 times 5 times 4 times 3 times 2 times 1. And we can write this function in a recursive way. So here's the factorial function as a recursive function. So factorial of n, if n is less than or equal to 1, return 1. Else return n times, well, factorial of n minus 1. So for example, if n is 3, factorial of 3 is going to return 3n times factorial of 2. So then it's called factorial 2, so we need to calculate that. Factorial of 2 is going to return 2n times factorial of n minus 1, or factorial of 1. So factorial of 1 is called, we need to calculate that. Factorial of 1, finally, we stop the recursion. Recursion has to stop at some point because n is equal to 1. It gets into that if case and says, hey, don't need to call factorial anymore, just return 1. So factorial of 1 returns 1 to this call, factorial of 2 that called it, so 1 times 2, and factorial of 2 can now return. So it returns its value, 2 times 1, which is 2, and then factorial of 3 can now return its value, 3 times 2, and now that's the final value that factorial of 3 returns. So that again, factorial of 1 returns, and then factorial of 2, and then finally factorial of 3 returns. So now let's write this recursive function in RISC-V assembly language. So here's our high-level code, our C code, and we know that our input argument comes into A0. It only has one input argument, in this case n, so that's an A0 when it's called. And so we're going to now just take it line by line and say, okay, well, if n is less than or equal to 0, less than or equal to 1, we want to return 1. So now we're going to branch if greater than. We're going to branch on the opposite case, A0, and we need a 1, so we're going to do some temporary register, add immediate T0, 0, and 1, and so now we can compare with that. Branch greater than A0, T0, then we want to go to the else block, right? So if it's greater than, the if condition wasn't true, and we want to branch over to the else block here. But if n is, so it's going to branch if it's greater than, but if it's less than or equal to 1, it will fall through, and we're going to get, well, return 1. We have to put our return value, which is 1, into A0. So we'll put that value, return 1. That's the value you want to put into our return register, where A0 is the return register as well. And then we're going to return JRRA. Okay, so now let's do the else block of code. Now this wants to return n times factorial of n minus 1. So first we have to make that call. So we have to call factorial of n minus 1. So first we're going to decrement n, add immediate A0, A0 minus 1. And now we're going to call factorial. Call it again with that new argument, n minus 1. And then we forget that this is recursive, because otherwise you can start looping around in your head. Once it returns, it will return to this location, right? That next instruction, once that that function call is complete, we'll return to PC plus 4, which is here. And then we want to multiply n times n factorial of n minus 1. So we know that factorial, the result of that call, right, the return value is going to be an A0. And n is also an A0. We're going to, suspend disbelief at this point. They can both hold n and the return value. We'll fix that in a minute. And let's go ahead and put this in our return value. So it's going to return n times factorial of n minus 1. So now it's going to say, okay, well, we're done there, kind of. We're going to fix it. Now return. And so there's our else block. This is our if block of code. And let's write that more nicely here. So here it is written more nicely. And now let's deal with the issues. So we've gone through the first pass and treated it as if it was just calling another function. We ignored the issues with the different registers that got overwritten, but now let's consider it. So now we've gone through the first pass. Let's consider any issues here. Well, first issue, A0 can't hold both n and the return value. It definitely holds the return value because that's what just got returned by that by the last call to factorial. So if we want to use n after this function call, then we better save it on the stack before the function call is made. And so we also know that there's an issue with RA, right? We know that, guess what? This is a non-leaf function. It's going to call factorial again. And so now we can add some code up here and say, okay, well, we need to make room for 2 words on the stack. So add immediate SP. SP 2 words is minus 8 bytes. Remember, it's growing downwards. So we subtract it. And now we're going to go ahead and store A0 on the stack and RA. So now we've preserved the value of n when factorial was called so that we can use it again even after other subsequent function calls. Okay, so we've got A0 and RA stored on the stack. And now, before we use n and RA, we're going to restore them. I'm going to show RA first, being restored from the stack. And then we did a kind of funny thing on A0. So that was our n value, right? When factorial is called, n is in A0. But we're going to restore it into T1, into some temporary register instead of A0. Why is that? Well, we don't want to overwrite what that last call to factorial returned. And so T1 is actually value n. And so now we have n times the return value. And we're going to put that in the return value of this function. And so we have to fix that one last issue of adding or restoring the stack pointer if we are in the if block. So we decrement the stack pointer by 8, store some registers, and then we can say, okay, well, if I get into the if block, I don't calculate anything, I just return 1, but I still need to restore the stack pointer before I return. Right? The stack pointer has to have the same value when the function call is made as when it returns. And so notice that when this kind of recursive call to factorial is made, we can put some addresses here at the top. So here's memory address hex 8500. Next instruction is at 04, 08, 0C, 10, 14, right, just sequentially. And this jump and link instruction occurs when PC is equal to hex 8524. So RA is going to be equal to PC plus 4, which is hex 8,528. So let's take a look at the stack and see what happens to the stack as this function operates. So let's suppose we're calling factorial of 3. So we're expecting to get 3 times 2 times 1. So the return value, eventual return value we expect to get is 6. And so there's the stack pointer has some value, ff0, just putting some value there. And this is before the call. And the first time it's made, this call is made, well, factorial of 3 is made, then we store those values, a0, well, we know what a0 is, it's n. And RA, we're not sure where it's called from. Wherever it was called from, that PC plus 4, so we don't put a value there. This is the value, and this is the register. The only thing we're actually storing is the value. I wanted to show you where it came from. And so then it calls jump or factorial again, but now the next call is with factorial of n minus 1, which is 2. And so that factorial function does the same thing, stores n, which is now 2, and now we know what RA is. It's hex 8,528 because it was called within that factorial function. And now after factorial 2 is called, then factorial of 2 is going to make another recursive call to factorial of 1, which decrements the stack, puts n on the stack, and RA. We know what RA is now, so we can put that value there. But n is equal to 1, and so that simply returns 1 and just restores the stack at that point. And so we can see as the stack pointer kind of gets rolled down, increasing the amount of stack space needed. So each of these stack frames, right, this is the factorial of 3's frame, factorial of 2, factorial of 1, and now we're going to roll them back and pop them off. Last in is going to be the first that pops off, the first out. And so here we have it rolling back up. So it's going to return a value of 1 and restore the stack pointer. Right, adds in this case 8 to it, 2 words. And then after that, so here's the return value, a0 that just got returned was 1. 1 times n are 2, and now it's going to return that value, in this case 2. And pop back up, another stack frame. This is the return value, a0. Here's our n. Multiply those together, put those in this function's return value. So a0 equals 6, and then restore the stack pointer. Add 8 to the stack pointer, and the return value is 6. So factorial of 3 eventually returns to its caller its return value, which is 6.